Okay, let's continue with the joy that is our scientific education. All right, so we were talking about heterogeneous equilibria. We have another one here. So for example, if I was going to look at the equilibrium constant for this one, again, we're still doing the products over reactants combination in concentration format. So you notice we've left the solids out. Again, you leave solids out, you leave liquids out. Gases and aqueous media is what you're putting into equilibria. You could also do the pressure version because again, if I leave the solids out, everything else is in gas. Now, if I had mixture of gas and aqueous, I'd have to use concentration. It's just representing equilibrium for in terms of pressures. You could also make that first one Kc, but most of the time K is taken to be the concentration expression. As we go through, you're going to see a bunch of different subscripts. So when we're working with acids, it'll be Ka. When you're working with bases, it's Kb. When you're working with solubility, it's Ksp. So the subscript usually denotes the what format you're working with. Okay, we've talked about it a little bit, but now we're going to look at reaction quotient. Again, this is the exact same equation as equilibrium. It's just at another point in the reaction. K is only at the equilibrium point. Q is going to be at any other set of concentrations. So for this one here, Q is going to be CO. Just like you would expect for the K expression. Except we just don't, like, this reaction is not at equilibrium yet.
Is there a way
There is. So sometimes you'll be given, like you may be given an equilibrium constant for a reaction because a reaction is always going to have the same equilibrium constant. You could calculate Q and compare the two. And as you would hopefully expect, there is also a QP. So again, just like you would expect for the equilibrium constant, except this reaction is just not at equilibrium yet, so it has to be reaction quotient. Gives you an idea of where the reaction is. One more sneeze and we have to perform an exorcism because you've done been blessed twice. It's not taken. So here's what we do. You have these criteria. If you're not, so if, like, for example, let's say you're asking, does the reaction need to go to the right? Does it need to go to the left, or is it at equilibrium? You can take your K and your Q and compare them. If Q equals K, then the system is at equilibrium. If Q is greater than K, so that means your products are on the top, your reactants are on the bottom. That means you have a higher concentration of products than is necessary for the equilibrium, meaning you have to shift to the left if Q is greater than K. So if Q is less than K, that's the opposite. You have too many reactants, you have to shift to the right. Because again, think of it. If Q is larger than K, you have too many products. The number on top is bigger. If Q is less than K, you have too many reactants. The number on the bottom is bigger. And that'll dictate which way the reaction has to shift to reach equilibrium. All right, so let's look here. So here you're given the equilibrium constant. And so here's your reaction, and you have these pressures in your system. Which way will the reaction shift? So you need to calculate Q, compare it to K, and figure it out. So your Q that's going to be 0.11, 2.0. This is going to give you a Q of 1.5 times 10 to the third. So is Q greater than, less than, or equal to K? Someone said it. Yeah, it's less than. So if Q is less than K, that means we have too many reactants. Which way will this reaction have to shift to reach equilibrium? To the right. And this is a comparison you can perform on any reaction if you're not sure. Come on now, don't be a bag of spare parts. Well, you're the one who started like the Letterkenny references. Letterkenny? Just your whole figure it out. Okay, watch Letterkenny, you'll get it. Canadian slang. Oh, yeah. Yeah, yeah. And what they always talk about the degens up north, and nobody likes ice fishing in Quebec. Shorzy, yeah. Shorzy's is a spinoff of.
I haven't watched that.
All right. Wasn't that Reacher before he was Reacher?
Yes.
Okay.
He's great. Whichever one made the cooling ice pellets. Oh, yes. That one. When they get overheated.
I saw the one where he talked about shooting up with rabies before every game.
Yeah. You know the Oreo?
No.
Oh.
Well, let's see if we can work through this problem. So we have a sample of S8. So that's a sulfur molecule, usually in a ring. Is placed in an empty rigid container at 1325 Kelvin at an initial pressure of 1 atmosphere, where it decomposes to S2 by the reaction. S8 becomes 4S2. At equilibrium, the partial pressure of S8 is 0.25 atmospheres. Calculate Kp for this reaction. So we know that our Kp PS2 over PS8. Okay. So here's the little trick to it. So we start with 1 atmosphere of S8. At equilibrium, there's 0.25 atmospheres of S8. So that's going to be your PS8 right there, your 0.25. I need to figure out how much S2 was created. Okay, so I say I start with 1 atmosphere. And I'm going to get 0.75 atmospheres of S8 was lost. Now, just like we've been doing with moles, your coefficients in your equation can be used for pressures. So that means so I have 1, let's see, 1 equivalent, whatever you want to call it, of S8 to 4 S2s. That is going to give me 3.0 atmospheres of S2 at equilibrium. So then we go to our KP expression, and we are going to take that 3.0 to the 4th over 0.25, and my KP is going to be 3.24 times 10 to the second. So that one had a little trick in it. You needed to figure out how much S2 was created. You could only do that by figuring out how much S8 was lost. And then you use, again, the coefficients in your equation. You can use those for moles, you can use them for pressures directly. Well, the power there is part of your, it's just part of your KP expression. So, I mean, it's just part of the equation. Your coefficients have to become your exponents in your equilibrium equation. Because you went from 1 atmosphere of S8 to 0.25 atmospheres of S8 at equilibrium. Right. And so that means you lost 0.75 atmospheres of S8 that became S2. And so at a 1:4 ratio, how much S2 is that? Well, it's 3 atmospheres. Okay. Now, let's see. Now we're going to start just looking at the process. I could have put a bunch of explanations here, but I figured working problems is the best way to do it. How to actually deal with equilibrium problems. So we have this reaction. We have our KP. In an experiment, we have 1 atmosphere of H2, 1 atmosphere of iodine gas, and 1 atmosphere of hydrogen iodide gas are mixed initially. So these are your initial pressures. At equilibrium, what is the partial pressure of hydrogen iodide? Now you've done this with concentrations. You can also do it with pressures. So let's start out by saying, so the first thing I'm going to want to do, and I'll show you why, is I want to calculate Q and compare it to K. All right. And so this will be 1 squared. So your Q is 1. You notice that Q is greater than K. So the reaction will have to shift left to reach equilibrium. That helps us fill in. We're going to build what's called an ice table. So for the columns of our ice table, we're going to need H2, I2, and hydrogen iodide. So our initial values, our initial values are those 1.0 atmospheres. The reason we figured out Q and we know it has to shift left is in this ice table, something has to decrease and something has to increase. We need to know which way that goes, okay? Now, it has to shift left, meaning we're going to get more H2 and I2 when we go to equilibrium. And that's going to be, so your change, the change leading up to equilibrium is going to be plus X, and then the HI is going to have to be a minus 2X because we have to shift to the left. Now you do that, it's real simple. You can take a look at your chemical equation there, and your X's are going to get the same coefficients as what's in your equation, okay? So that means at equilibrium, you're going to have a value of 1 plus X, 1 plus X, and 1 minus 2X. These little expressions in your equilibrium row, those are your equilibrium pressures. You have to solve for X, plug it in there, and figure out what those equilibrium pressures are. Okay, so our KP same expression, except this time we're going to plug in those equilibrium values. So that's going to be and this is going to equal 0.010. Now I know this looks like a lot of fun to solve. Now there's a couple ways you could go about this. What's the longest path to take to solve this? Yeah, so you'd have to do the FOIL method on the top and the bottom. Then you have to get an equation and turn it like a quadratic, set equal to 0, and then use the quadratic formula. You could do that. Although sometimes paying attention mathematically helps out because you're very, very lucky here. Because I have 1.0 minus 2x squared over 1.0 plus x squared. What can I do? Not cancel. Yeah, so I can square root everything here. So when I square root everything, this is going to give me and this is much easier to solve. So now I want to multiply through by the denominator. That's going to give me 1.0 minus 2x equals 0.10 plus 0.10x. And then I solve for x. So let's see, if I take the 0.1 to the left and the 1.0 to the right, I'm going to get a negative 2.1 x, negative 0.9, which just becomes 2.1 x equals 0.9. And then your x, you're going to divide through by 2.1 becomes 0.43. Now, the pressures at equilibrium, let's see, it was just one of them, I think. Yeah, HI. So the equilibrium pressure of HI, if you remember from the table, is your 1.0 minus 2x, because you see that's your equilibrium value right there. It's going to be 1.0 minus 2, 0.43, and that's going to equal 0.14 atmospheres. Yep.
So if I squared or I don't know, whatever it was, a product that it still shifted left, would the C be plus 2x and then minus x and then minus x?
If it shifted to the right,
No, if it was still to the left, but if I squared was or I2 was product.
well, that's all dependent on Q versus K. So it depends, again, you could have any chemical equation. Calculate the Q, compare it to the K. That's going to tell you which of these is plus and which is minus. If it shifts to the left, your reactants have to be plus, your products have to be minus. If it shifts to the right, your reactants have to be minus, and your products have to be plus.
But it feels like the exact same scenario where it was shifted to the left, but you only have one reactant, would the H2 be?
But yeah, so for example, if I was a product and only H2 was on the left, then only H2 would be plus, the other two would be minus.
Or would it be plus 2x or just plus x?
The H2?
Yeah.
If it had the same coefficients, it'd be just plus X.
Then you get minus the 2x because of x.
Yeah, because you have the two HI.
Okay.
Yeah, yeah. So like, let's just say in some weird scenario, it's H2 arrows I2 plus 2HI. That'd be plus X for the H2, minus X for the I2, minus 2X for the HI. Okay. So kind of a step-by-step of how to solve these. You always want to look at your balanced equation. You want your equilibrium constant expression, set up your ice table, calculate Q, compare it to K if you need to. When we're working with acids and bases, that's usually much easier because like when you're looking at an acid dissociation, your products usually start at 0. So you automatically know which way everything's going to go. So if you have anything that's a 0, well, it's going to go that way. Let's see, and substitute into the expression for K and solve. History fact, did you guys know that there was a bear who was a corporal in the Polish army in World War II? No, I'm not kidding. There was a bear who was a corporal in the Polish army in World War II. But we're going to do another one. Okay, so at 25 Celsius, we have an equilibrium constant of 0.09 for this following reaction. Calculate the concentrations of all species at equilibrium for each of the following cases. A, 1 gram of H2O and 2 grams of Cl2O mixed in a 1 liter flask, and D, 1.0 moles of pure HOCl placed in a 2 liter flask. Okay, so the K value we're going to be working with is going to be that. Now, these are all concentrations though. Yeah, so we're going to need concentrations in moles per liter. Okay, so first we have 1.0 grams of H2O. How do I change this to moles? Yep, so I need the molar mass. Grams per mole. That's going to give me 5.5 times 10 to the negative second moles. And then my concentration of H2O. So we have 5.5 times 10 to the negative second molar. We have to do the same for the Cl2O. I'm going to incorporate this all into a single calculation just to show you can do that. Does anyone know the molar mass of Cl2O? And this is going to give you 2.3 that's 10 to the negative second moles per liter or molar. Okay, now we have initial concentrations. This one we don't have to calculate Q. Why is that? We already know which way the reaction is going to proceed. Look at my scenarios there. What do I not have at the starting scenario? No product. I have no product to start with, so that's going to be a value of 0 in the ice table. If I have a value of 0 in the ice table, the reaction's always going to go that way. I can't go the other way. I can't end up with less than nothing. That's also why when you're using the quadratic formula, if you get an X value that produces a negative concentration, you just have to drop that X value. It doesn't make sense. You can't end up at less than nothing for a reaction. That's kind of true. When I was an undergrad, I did end up with a negative % yield in my organic chemistry class. We were doing a distillation. You're supposed to distill off a lighter chemical. We're supposed to have stuff left in the flask. I ended up distilling everything. I had nothing. So you see here how I have H2O and Cl2O. I'm only mixing reactants to start with. I have no products to start with. So that's going to have to be an initial value of 0. That means this is going to have to go to the right. So I don't even need Q. The ice table. Okay, so we have H2O, Cl2O, and the 2, HOCl. My initial values, 5.5 times 10 to the negative second, 2.3 times 10 to the negative second, and 0. That value of 0 is what tells me I have to go to the right. The change that's going to happen. I went ahead and brought these down with their coefficients to make it easier. Minus x plus 2x. My equilibrium value those are my equilibrium values. Now I need to put these inside of the expression for K. Okay, so products over reactants. So we're going to have 5.5. And then, so the concentration on top is squared. There's our expression. Oh yeah, we use the full system on this one. Okay. So someone foil the bottom and tell me what you get. I would be surprised if you could do it in your head, even those of you who took Tim Keith's class. Yeah, it is. It is. It's going to be. It's like that episode of Rick and Morty. What's the square root of this number? It's at least 40. Ice tables will become very familiar to you because it's what we're going to use for the rest of the semester. You're just going to do a lot of these. You're going to do it in terms of general reactions, in terms of acids, in terms of bases, in terms of buffers, in terms of solubility. And did you guys memorize your solubility rules last semester? Okay, so when we do solubility product constants, you'll see why they are the way they are, because the value of your K tells you how soluble the salt is. Remember, a big K means it's very, very soluble. And even on the list where it says insoluble, nothing is truly insoluble. It's just mostly not soluble. What do I get for a quadratic on in the denominator? Yes. Close. Your last one should be something like, well, 1.3 times 10 to the negative third. So yep, so that's what so same thing. So 0.078 and that's X. Yeah, 1.265 or 1.3 times 10 to the negative third. What do we have on top? 2x squared. What does that become? 4x what squared? Remember, that's going to equal the 0.090. That's the K we were given. Okay, now we're going to multiply the denominator through. No, no, because the x squared in your denominator is buried inside of an equation. So you can't cancel it out. Okay, so what, 0.090 x squared, 7.02, 10 to the negative third, x, and then 1.17 to the negative fourth. And now I want everything on the left side of the equation because I want a quadratic equals 0, so I can use the quadratic formula. So when I move everything to the left side, and now I can use the quadratic formula. And much to the eternal pain of most students every year, that plus minus means you have to do the calculation twice. One time adding, one time subtracting. Unless some calculators now will do both operations at the same time, but if you can get it to work, great. Otherwise, be careful. However, if any of you are willing to write a computer program that can solve this for you, you can bring it to your exam. I don't care. I don't care what language you use. I don't care if you use Python, Fortran, uh, R, Java, Ruby. I don't care. Nope, absolutely not. That's cheating. You have to write it yourself. So your 3.91 is your A, your 7.02 times 10 to the negative third is your B, and your 1.7 times 10 to the negative fourth is your C. All right, so means X is going to equal a negative 7.02 times 10 to the negative third. To do this calculation twice. Okay. Squared is 4, 3.91, negative 1.17. Just remember, I will check your code. And there are very noticeable differences between people who are experienced coders and those who are not. You're experienced? So when you solve for this, you're going to get a value of X equals 4.6 times 10 to the negative third, or negative 6.4 times 10 to the negative third. Now, let's keep in mind that one of our equilibrium values is 2x. Okay. If I put in a value of that's a negative X there, I end up with a negative value for my equilibrium concentration for my product. That makes no sense. So that value's out. So you have to use the 4.6 times 10 to the negative third. Okay, so at equilibrium, that's your H2O, Cl2O. So those are equilibrium concentrations. Now that way was the full way to do it. You could solve all of them this way and ensure you get the right answer. There are times when you could make assumptions, or you could notice that the math makes things easier on you. Let's see a time when the math makes things easier on us. How much space do I have left? Oh, I should have plenty. Okay, so for part D, let's go back up and look. 1 mole of pure HOCl placed in a 2-liter flask. Okay, you see I'm starting with all product this time and no reactants. So that means it's going to have to go that way. That's our initial concentration. Remember, your 0 subscript means initial value. So our initial values are 0, 0, and 0.5. My change, I'm going to have a plus x, and a minus 2x. My equilibrium value will be x, and 0.5 minus 2x. Okay. My k value is going to be 0.5 minus 2x squared over x times x. That's going to be 0.5 minus 2x squared over x squared. How did we luck out this time? Yep, I can square root everything. So, and this whole thing will equal the 0.090. So, all right. So now I'm just going to kind of flip sides here. I'm going to have a 0.30x equals 0.5 minus 2x. We're going to add 2x to both sides. 2.30x, 0.5. X is going to be 0.217. Okay, so at equilibrium, as you saw at equilibrium, those were both just X. And that's going to be 0.217 molar. Let's see, your HOCl. That's going to end up being 0.07 molar. So that one ended up nice and neat. Okay. Now we're going to make it through this last one. We may not make it all the way through Le Chatelier's principle, but that's just reading. Like you can look at that. It's real simple. It's how you unbalance an equation and how it adjusts. Okay. One of them I know some of you had trouble with last semester, endothermic and exothermic reactions and adding or taking away heat. So when can we make approximations to solve for X? Well, you notice how my K value here is very, very small, 10 to the negative 6. You can start to make this approximation below, like smaller than 10 to the negative third. Anything 10 to the negative third and above, you really want to do it the other way. There's also a thing called the 5% rule where you can test your approximation to see if it works. And then I'll show you what that means. Okay. So very small K values is where we can start to approximate. Okay, so 2 moles of CO2 in a 5-liter vessel. That's going to give 0.40 molar as my initial concentration. And let's build our ice table. CO2, CO, O2. The initial value 0.40, and then 0 and 0. The change minus 2x plus 2x plus x equilibrium. Okay, so our K value. That is going to equal 2x squared times x over 0.40 minus 2x squared. That's going to equal our 2.0 times 10 to the negative 6. This is the approximation I'm talking about. When your K value is very, very small, that 0.4 minus 2x is going to be so small, it'll make almost no difference to the 0.4. So we can get rid of that. We can approximate that to just 0.4. Okay, so what you end up with on the top, you end up with 4x cubed. On the bottom, 0.40. So you see, I got rid of the minus 2x. Because again, that K value is so small, it's not going to make a real difference. So yeah, you do. Okay. So let's see, you're going to solve for x. You're going to end up with an x of 4.31 times 10 to the negative third. And so you say, is this valid? 5% rule. And if this is less than or equal to 5%, your approximation is valid. So for this, you're going to get 4.31 10 to the negative third over 0.40 times 100. You end up with 2.2%. So this is a valid approximation. And so then at equilibrium, you just fill in X for each one of these. Okay. So that's the approximation. When you have a very small K, you can go back up to this part right here, and you can drop off that minus 2x or minus x or whatever it is, because it's going to be so small. And look at the end, your CO2, your 0.4 minus 2x still ended up at 0.39. See, it's very, very tiny. So it's essentially still just 0.4. So you can drop the minus 2x off. And a good dividing line is going to be that 10 to the negative third, 10 to the negative fourth line. Otherwise, perform the 5% rule. Keep in mind at the end here, we have, I laid out Le Chatelier's principle. And that's just reading. It should be pretty straightforward. Just read through that. Make sure you understand how that works. There will be on the one I make Friday. I want to make a new, there's not one on this current one.
Say for the C.